Hello everyone, welcome back to my online course on chemical applications of group theory. So this is my first video lecture apart from the introductory video lecture on the course structure presented previously. So if you haven't go through my introductory video which explains how the course is organized and what are the references and all, please go back and watch it before proceeding to this lecture series. So the title of my course is Chemical Applications of Group Theory, and today in my first lecture I'll be talking about the foundations of group theory and molecular symmetry. This lecture comes under the module 1 and it is the first lecture in the module. Now this course is available in two platforms. One in Moodle platform of Government College Madapalli, and the link is given here. Another one in my YouTube channel, and the channel link is also provided here. Now the courses are updated in my personal profile and its link is given here. You can find these links in the description box as well. The detailed syllabus on the course is also available in my course updation page. Let us start looking at first part of this course, namely Foundations of Group Theory and Molecular Symmetry. So as I have told you earlier, our main focus of this course will be to discuss the chemical applications of symmetry using the mathematical principles of group theory. Our entire course is then to show how an understanding of the symmetry facilitates the understanding of science, particularly in chemical science. Now let me ask a question. Did you ever thought of why symmetry is important in nature? You could find countless examples of symmetry that nature provides us if you look around the nature. Coming to this example, I have a flower here. On one side I have a flower and the benzene molecule on the other side. Now look at this flower and benzene. You could find a common property among these two. They have similarity in symmetry among each other. Say for example, if you assume an axis passing through the center of the flower and center of benzene, if you rotate the flower as well as benzene at an angle of 60 degrees, you will end up in a configuration that is indistinguishable from the original one. We would say both of this flower and the benzene has a rotational symmetry if you rotate it through 60 degrees. Coming to the case of benzene in a little more detail. So this is the benzene molecule, it's the three-dimensional structure. Now if you consider an imaginary axis passing through the center of the molecule, and this imaginary axis in symmetry terminology it is called a C6 axis, about which you will learn in later class. Now if I rotate this molecule through this axis by 60 degrees, you see what happens. Now it goes to a configuration that is indistinguishable from its original configuration, and this is called a symmetry operation. We will discuss all these symmetry operations and symmetry elements in the next lecture. Now why are we studying group theory and symmetry in chemistry? There are many reasons. The first reason is the concept of group theory, that is the backbone theory that we are going to study, applied to chemistry greatly simplifies the calculation, particularly the quantum chemical calculations. And in many places in chemistry you might have been noticed the atomic and molecular orbitals are labeled in a particular fashion. And the basis of this labeling comes from group theory. So let me now point out some of the important applications of group theory. As I told you earlier, the concept of group theory when applied to chemical problems greatly simplifies the calculations. Now you might have seen in many chemistry textbooks the way atomic orbitals and molecular orbitals and their energy levels are labeled in a particular fashion. The basis of this labeling actually comes from group theory. and it also provides a qualitative information about the possibility of transition between these energy levels in terms of an integral known as transition moment integral, about which we will learn in later classes. And this leads to the formulation of a set of rules in spectroscopy called selection rules, which predicts a transition between one energy level to another energy level. Another important application is in the case of Woodward-Hoffmann rules. That is particularly important in organic chemistry, and you might have seen Woodward-Hoffmann rules in the perspective of organic chemistry, which we shall discuss it in terms of group theory. And another area is in the chemistry of transition metal complexes. The theories governing transition metal complexes like crystal field theory, ligand field theory is very well aided by incorporating group theory into it. So let us see the definition of a group. A group in mathematical sense is any set or collection of elements which, together with some well-defined combining operations, which in our case is a binary operation, obey a certain set of rules. And if you look at the definitions, you can see there are some words that needs more clarification. And these are the collection, elements, combining operations, and rules. So let's see each term one by one. A collection here is simply a specified number. So a group will have a specific number of elements. Then comes the elements. The elements are none other than the constituents of the group. And then comes the combining operations. This is the most important term in group theory and is the basic law which defines the combination of two or more elements. So these are the basic law which defines how two elements are combined. Now in the case of elements, these elements can be a set of numbers, it can be a set of matrices, it can be a set of symmetry operations that we will see in the next module. And while discussing the group, nature of the elements in group theory is not that important. Element may be a group of matrices, a group of numbers, or a group of symmetry operations. But the nature of the element is not important. What is important in group theory is the consequence of the law of combination of elements in the group. So to qualify a group to be a mathematical group, there should be a collection of elements and there should be some combining rules which governs the combination of all these elements. So naturally the next question you will ask is, what are these rules? So let us discuss these rules, and the first among them is the existence of identity, or otherwise it is called identity rule. So what is this identity rule? This rule says every group must contain an element which commutes with all other elements and leaves them unchanged. So there should be one element which commutes with every other element and leaves the other element unchanged. And the identity element is usually represented by the symbol E. Say for example, suppose I have a group which contains 4 elements, namely E, A, B and C. This set of elements or group of elements is usually represented within a curly brace like this. So you can immediately say E is the identity element if the following set of equation is valid. E combined with A should be equal to A combined with E. It should leave A unchanged. Similarly for B and C. If all these three equations are valid, then we say E is the identity element. That is, when identity element combines with every other element, say for example, if the element is R in a group, it immediately gives back R, that element. So the identity element which does not change any other element in the combination process. Say for example, if I have a set of numbers 1, I, minus I and minus 1, where I is the imaginary number and the combining operation is multiplication. So immediately you can say that the identity element in that group is definitely 1. 1 is multiplied with any other element, leaves the other element unchanged. And thus the identity element here is 1. So in this group of 4 elements, we have 1 which is recognized as the identity element. This identity element is also called unit element. So then comes the second rule, which is called closure rule. This rule says the combination of any two elements in the group must produce another element or same element back. If you are getting another element, then that element should also be a member of the group. Now let's bring back the same example. Now we have 4 elements and the combining operation is multiplication. See, it's not necessary that the combining operation should always be multiplication. It can be addition, it can be matrix multiplication, it can be a combined operation between two symmetry operations, etc. Take any two elements in the group and combine under multiplication. You can see that 1 into I is I into minus I is 1, minus 1 into minus 1 is also 1. Likewise, if you take any combination within the group, you could get the result. And you see the result I, 1 and 1, all these 3 elements are elements of the same group. So this rule says, if P and Q are the 2 elements in a group, then the combined operation represented by PQ should also be an element in the group. So if I combine the 2 elements as PQ, and when it is combined, if I am getting another element R, and you should always remember the combination does not merely means multiplication, as I told you earlier. So it could be a matrix addition, it could be an addition between two natural numbers, etc. So a combination does not merely means multiplication. Now if I combine the two elements as QP, which need not necessarily be equal to R in general, that means P and Q, that means it is not necessary that P and Q commutes unless one or both of the element is identity element. This is because the elements are sometimes matrices and these matrices may not in general commute with each other. So if Q and P gives R prime, then this rule says that R and R prime should also be a member of the group. Thus in short, according to this rule, any combination of a pair of members is a member of the same group. So that is about the second rule. And then comes the third rule. This third rule says for each element in the group, say for example, if the element is R, there must be a reciprocal of the element R, which is written as R inverse, such that the following equation should hold. This R into R inverse should be equal to R inverse into R, which should be identity element. And this R inverse should also be a member of the group. So you should always keep in mind the R inverse should not be from outside the element. This R inverse should also be one of the element in the group. So this equation essentially says if you have an element R, there should be a partner of this element R inverse such that when this R and R inverse are combined, the result should be identity element. This rule immediately says there should be identity element E in all mathematical groups. Let's bring back our old example with 4 elements 1, I, minus I and minus 1. Now take any element and find out the inverse of that element. You should keep in mind the equation R into R inverse should be equal to E, and which is equal to R inverse into R. And this R inverse should also be a member of the group. Let me ask what is the inverse of I. So let's try with minus 1. If you combine I with minus 1 under multiplication, it gives minus I. The result is not identity. Minus 1 is not the inverse of I. Whereas if you multiply I with minus I, you are ultimately getting 1, and we know that 1 is the identity element in this group. So minus I is the inverse or partner of the element I and vice versa. Similarly, find out the inverse of other elements in the group. So what is the inverse of 1? Inverse of 1 is 1 itself. And you will see that in all cases, inverse of identity element is always identity element itself. What is the inverse of minus 1? Inverse of minus 1 also is minus 1 itself, because when they combine, they gives identity element. So it says inverse of an element can also be itself. In the case of identity element, inverse of identity is always identity, but it is possible that inverse of any other element can also be the same element. Now let's come to the rule 4. This rule essentially says the associative law must hold for all elements. Say for example, if I have 3 elements in the group A, B, C, when the elements in this group are combined, this associativity rule essentially says the following equation must hold. What are these equations? AB combined with C should be equal to A combined with BC. That is, this rule says the order with respect to parenthesis is immaterial. Now suppose the combination of AB gives P and the combination of BC gives Q, then this rule says ultimately P combined with C should be equal to A combined with Q, and P, Q, C should all be the member of the group. Now let's bring back our previous example of 4 elements, 1i, minus I and minus 1, and the combining rule is multiplication. You try to prove the associativity law here. Say for example, if I take the 3 elements 1i and minus 1, you can definitely see that associativity rule is valid here because they are numbers. When 1 combined with I and I combined with minus I, the 2 elements that got are different, but both of them are elements of the same group. But when we come to the case of matrices, this becomes more complicated, and we will discuss all those things shortly. And these are the 4 rules for any group to qualify as a mathematical group. And you see that the example so far we have taken is a group of 4 elements. Group of 4 elements under multiplication obeys all rules of a mathematical group, and hence it qualifies as a mathematical group. Now there is another term which is called order of the group, which is usually represented with the lowercase letter h, which is none other than the number of elements in a group. In the previous example, the order of the group is 4 because there are 4 elements in the group. Now if I ask a question, how many binary operations are possible with these h elements? H is the order of the group. So immediately you can say there are h square combinations possible. So in our previous example, There are 16 combinations possible because h is equal to 4. 4 square is 16. Now, how we will represent all these h square combinations in a neat way? So let us construct the table with this example: 1i minus in minus 1. So what you have to do is, you have to label the first row as your elements 1i minus in minus 1, and first column also should be the same element in the same order, 1i minus and minus 1, and you should keep writing the identity element as the first element. It's a convention. So that is the column header. And this is the row header. And now start combining all elements. Say for example, if I take the column element minus 1 and the row element minus I, you can write this intersection in two ways. First, minus I into minus 1, as well as minus 1 into minus I. In this example, the answer you are getting is same in either ways, but this becomes a problem if your elements are matrices, because matrices in general do not commute. And therefore, we should follow a convention while constructing this table. So the convention I followed in all my lectures is as per the convention followed by F.A. Cotton's book. So this is the convention. Column element multiplied by row element. You should not write the other way around. So AB means A is the column element and B is the row element. You should not confuse this, because some other books uses the just other way around as their convention. If you follow one convention, you should always stick on that convention, then it won't become a problem. So AB, suppose you are getting R, this means that at the intersection of the column labeled A and the row labeled B, we find the element R, which is equal to AB. Now if you come back to the table, that element at the intersection is minus I into minus 1. And we follow the convention and find all other combinations. I remind you that in this case, if you write in either way, it doesn't become a problem, because all are numbers and numbers in fact commute with each other. So for this, you don't find any big deal in this, but later it becomes a problem when you deal with representation of asymmetry operations in terms of a matrix. So first row is fairly simple, because one element is identity element which commutes with every other element. And similarly, the first row also is fairly easy. You can simply copy the same header down. Now, if you start filling the other elements, other combinations also, you will get this result. So, if you do an analysis of the elements in a table, you will end up with the following observations. The first observation you make is each row and each column contains every element in a group. If you see the table, you see that if you take any row or any column, you could see that every elements are present in every row or every column. Now, what is the second observation? No two rows or columns are identical in the distribution of elements. That is, if you watch elements along a row or along a column, you see that no two columns or rows are identical in the distribution of elements. And the third observation you can arrive at is each row or column is a rearranged version of group elements. And the fourth observation is no elements other than the group elements are present in any row or column. This leads to a theorem in group theory which is called rearrangement theorem, which says each row or each column in a group multiplication table lists each element in a group once and only once. Thus, each row or column is a rearranged version of group elements. Let's take the previous example. You see that no two rows or columns are identical. If you take any row or any column, you can find every element in the group, but each element appeared only once. And you cannot find any element other than group element in the table. And this table is called group multiplication table in group theory. Now let's take a little different example in which I have 6 elements E, A, B, C, D, F. And each element is a 2 by 2 matrix, and the combining rule is matrix multiplication. So what are these elements? Of course, E is an identity element, and the elements are 1, 0, 0, 1. A element is minus 1 by 2, root 3 by 2, root 3 by 2, minus 1 by 2. Now B element is similar to A, except that the matrix element differs only in sign. The C element is 1, 0, 0, 1, again diagonal matrix. D element is also similar to B, but differs only in sign. Now construct the group multiplication table. Here we have 6 elements, so the order of the group is 6, and hence there are 36 combinations possible. So the first row is pretty easy because it is simply the multiplication of each element with identity element. First column also is easy in the same way because one of the element is identity. Now, so suppose I want to find out the combination of matrix C and B. So in our convention it is C multiplied by B. So C matrix is 1 0 0 minus 1. B matrix is this. Now we have to do almost 25 matrix multiplication, and it's not very easy to do that, but if we use some softwares we can do it much quickly, and hence from here I will use a software called Mathematica which will give the matrix product very easily, and I have written a function in Mathematica that would identify the product matrix from the list of matrices that we have in our group. So let's go to the Mathematica and see how this matrix multiplication is done. Okay, now let me take you to a program that can be used to very easily compute the matrix based group multiplication table. Since in group multiplication table we have to do many matrix multiplication, it will be very useful if you program it in some way. So I have written a program in Mathematica software that could find out the matrix multiplication very easily, and that will tell you what is the product of two matrices and where this matrix is positioned, which is that particular matrix, whether the resulting matrix is A matrix, B matrix or C matrix, etc. So you have seen on the right hand side, this is the group multiplication table that we have to construct based on the matrices E, A, B, C, D, F. And what are these matrices? This is the identity matrix. I am using lowercase letters because some capital letters are reserved in Mathematica, so I cannot use it. So I am using lowercase letters for identity matrix. This is the matrix that has been defined in Mathematica, identity matrix. This is the A matrix, B matrix, C, D, F matrices that you have seen earlier. And then what I have done is, I have created an array of matrices. This K is an array of matrices which contains 6 elements. All these 6 elements are our elements in the group E, A, B, C, D, F. Now I have written a little lengthy subroutine called match mat that takes 2 arguments. One K, which is actually an array of matrices that we have just defined, and the product of two matrices. S is the product of two matrices. Suppose, say for example, come to this table on the right hand side. Suppose I have to get the product of B and C, which ultimately I should get F, right? So how to identify the product? So this function will evaluate the product and will tell you which is the product in the group multiplication table. So let us do a simple exercise. Let me first carry out the operation without my function. Say for example, I want to do the matrix B multiplied by C. This is how you have to write it in Mathematica. If you write B dot C, it will give you the product of B matrix and C matrix. You got the product as this one. Now you have to go back and compare these matrices and find out which is this matrix. If you see closely, you would see that it is exactly F. It is exactly F. And this is what we have got in group multiplication table also. See B and C, the result is F. So the resulting matrix of B and C is this. What is the B matrix? B matrix is this. And what is the C matrix? C matrix is the simple diagonal matrix. And multiplying this, you got this result. So if you look at the group multiplication table, multiplication of B and C should give F. So let us go back and see what is F. F is this. And you immediately realize that you have got the same result. B and C is F. But this is a tedious process because each time you have to compare the resulting matrix, go back to all the 6 matrices and see which is this product. This is not an easy task if you have more number of elements as matrices. Say for example, if you have 12 matrices, then this is not easy. That is where my function, user-defined function match comes in. Now see, if I do the same thing, what you have to do is, you have to type the function name match. This is already there. Now put a bracket. Then the first argument is the array of matrix, that is K. There is K here. See, this is the array of matrices that is being given, K here. And second argument should be the multiplication, B dot C. So second argument should be a matrix. That matrix is this. Actually we are inputting this matrix. So simply we are giving B dot C and close the bracket, press enter key. So you got a kind of truth table, whether it gives true or false. So in the F, in red color, you see that F is true. That means this matrix is an F matrix. So you don't have to go back and compare all those matrices. If you have some 24 matrices, it would be very difficult for you to find out the resulting matrix. The comparison would be a tedious process. Now let's take another example. Say if I do this, on the right hand side, if you see the group multiplication table, this B comes from D dot F. So what I have to do here, I have just copy this and paste it here. I just have to change this to D dot F. Now if you press enter, see the truth table comes in and gives you the answer B, where all others are false. So the answer is B and it is the same result that I have got. In the same way, you can do all other calculation much more quickly with my user-defined function. I can share this with you. You can play with it if you have Mathematica software. And this is the way Mathematica becomes much more useful for matrix computation. There are many other softwares as well. I will introduce some other softwares also during my classes. Okay, that's all done. Now in the end, suppose that if I enter a matrix that is not in the list, that is none of these elements E, A, B, C, D, F, then what this subroutine will give? Let us test it. Say if I enter some matrix Q that is equal to, say this is there in the list, but if I give negative here also, all elements are negative. This is not in the list. If you go back and see, there is no matrix in which all matrix elements are negative. So this is not in the list. Now if I input this Q matrix in match, let's see what happens. K, Q. Then you see you are getting an error message saying the matrix is not found in the list. That means you are not allowed to enter a matrix that is not in the list. This is the way this subroutine, this function is programmed. That's all about this program. Alright, now if you come back from Mathematica, you see that we have got the matrix product CB, which is exactly equal to the D matrix. And the combination BC, which is given as minus half minus root 3 by 2 minus root 3 by 2 and half, which is exactly equal to the matrix F. This we have seen in our calculation, and we see that the combination BC is equal to F, and combination CB gives D, and hence they do not commute with each other. So the combination BC gives a matrix which is equal to F, and the combination CB gives D, and immediately you see that the matrices do not commute. And if the matrices do not commute, that is, if the elements in a group do not commute, such type of group is called non-abelian group, about which we will see later. Now the remaining matrix combinations, you can do it as an exercise. If you have Mathematica, you can do it very quickly. You don't have to do manual calculations. Just to put in that function matmatch, you will get the result. Now if you start filling the other elements in the group multiplication table, you are going to get a table of this kind. Now please verify that whatever I have written here for the group multiplication table obeys rearrangement theorem, in which I have not duplicated any element along the row or along the column, and you have to make sure that every element is present. I have prepared a Microsoft spreadsheet that's a kind of game that can be used to fill all the elements without any mistakes. It's a kind of game, you can do it. I will demonstrate that game in a short while. Now if you don't have the access to Mathematica, and if you want to make sure that whatever you did is perfectly fine, I had prepared this spreadsheet so that you can do it as a game. In the end, if you do it correctly, you will succeed the game. Otherwise, you can go back and correct it. It's a very simple and funny game. So let's go back to the spreadsheet and see how that spreadsheet works. Okay, now this is the GMT constructor game. This is a very simple game developed by me and is particularly useful when you want to prepare a group multiplication table without any mistake. So I have made an example with a mathematical group of order 6. There are 6 elements. If you look at the window, there are 2 tables. One table is for constructing group multiplication table, and the 6 elements in this group are E, C, T, A, G, J. So you have to make a group multiplication table here. What all you have to do is fill all these rows and columns, and you should always keep in mind the rearrangement theorem, which says every row or every column should be a rearranged version of group elements. This game also will indicate where you have made a duplication along the row or along the column by changing its color. Say for example, if I enter the first row, entering first row and first column is particularly simple because you have an identity element on one side, and this identity element commutes with all other elements. Immediately you can write the first row E, E, C, T, A, G, J. That is proper, that is fine, there is no mistake, so there is no change of color. If you note down the change of color, then that indicates that you have made a mistake. Now, if I fill the second row as C, E, J, G, A, T, Now there is no change in color, which means that you have done it particularly fine. Now if I change the element j to g, you see what happens. Then immediately you see that there is a change of color. Adjacently there are two elements, both are same, and that is against the laws of group multiplication table, and you have to correct it. So this way this program will notify you if you have made any mistake. So I am going back, changing g to j, then it's fine. Now in the third row, if I start filling, say now first element is of course t, g, e, j, c, a. It's all fine, you have not made any mistake, so you are not getting any errors. If instead of j, if I write it as c, immediately you see that you have made a duplication along the row. 2 c's comes twice, and immediately the game will notify with the change of color. Now I'm correcting it. Now instead of j, if I type a, then you have made a duplication along the row as well as along the column. You see, along the column you have made a duplication of element a. Along the row you have made the same duplication a. So in this way, if you make any mistake along the row or along the column, the game will immediately notify you that you have made a duplication. If instead, if I type a again, this a will also be notified. Now you go back and correct it. The third column is done. Now there is a matrix which I set alien matrix, and see what is this alien matrix will do. Now come back to this group multiplication table. If instead of g, here instead of g, if I input k, then you see that the k is not an element in the group, and this will be immediately notified in the message as well as in the alien matrix. See, there is a message that alien found, and where this alien is positioned is given in this alien matrix. See, there is the cell that changes the color to red. So this second column and third row. So if you go to the second column and third row, this is k. You can find the position of the element that is not in the group using the alien matrix. So in the case of group multiplication table of order 6, it is very easy, but assume that you have to prepare a group multiplication table of order 24, which is the case of methane molecule, which has all 24 symmetry elements, and assume that you have to prepare a group multiplication table of 24 elements. This kind of game will be particularly useful in that case. So I am changing this back to G, then that message disappears. Now in the fourth column, first element is A, second, if I type J, G, E, T, C, then it's all fine. In the same way, you can fill all elements in the group multiplication table. If there is any mistake, if there is any duplication along the row, it will be indicated by one color. If there is any mistake along the column, it will also be indicated by another color. And if you make any wrong input by entering an element that is not in the group, this will be notified immediately in the message box, and the position will be notified in the alien matrix. Now this is a simple group multiplication table constructor game. Now you can do an assignment by extending this group multiplication table of order 6 to some other number, say 12. If you are familiar with Excel sheet, you can immediately extend this group multiplication table to whatever number you want, and that's about my group multiplication table game. Now consider from the previous example, if you take only the first three elements, that is in the yellow box, you will see that these three elements itself form a smaller group. And such a group is called a subgroup, which obeys all properties of a group multiplication table, which obeys the rearrangement theorem. You can check and verify it. So this subgroup is of order 3 and our main group is of order 6. So I will stop this discussion with another simple example that we have seen previously, the 4 numbers. And if you take the first and last number, that is 1 and minus 1, and all the combinations, and make another smaller group multiplication table, you will immediately get a subgroup of order 2. And you might have noticed that a subgroup always contains identity operator. In the last 2 examples, you might have seen first example is a subgroup of order 3 which contains identity element, and the second example is a subgroup of order 2 that also contains identity operator. So this is the necessity that a subgroup should always contain identity operator. And another point is the order of the subgroup should be a factor of the order of the group. That means if you divide order of the group by order of the subgroup, you should always get an integer, you should not get a fraction. So in the above example, we have a subgroup of order 2 and the main group is of order 4, and we are getting 2, an integer. If you are not getting an integer, that means you have made some mistake. Now let me discuss the various types of groups. In fact, some of them we have already discussed, like non-abelian and abelian groups, but we will explain all these in a little more detail here. Let me discuss the first one. First one is the finite and infinite groups. This differs in terms of the order of the group. So if you have a finite number of elements in a group, such a group is called finite groups, and H will always be a finite number. But if you have an infinite collection of elements in your group, then such group is called infinite groups, and H is usually infinity. We will first see an example for infinite group. A group of all integers starting from minus infinity to plus infinity form an infinite group with the algebraic addition as combining rule. That is from minus infinity to minus 3 minus 2 0 plus 1 plus 2 plus 3 etc. up to infinity, and the combining rule is algebraic addition. So immediately you can ask which is the identity operator here. So identity operator here is not 1, here it is 0, because when you add any number to 0 you will get that number back. And how do you find the inverse? When you take any number and adding with another number that gives 0, so it should be exactly the negative of that number, and that negative of that number will be the inverse of that number. Now the second type of group is abelian group. We will now take the previous example of 4 elements. 1, I, minus 1 and minus I, and if I copy the group multiplication table for that, here you can see that every combination is commutative. Now you take any two elements and combine them as per the combination rule, which is multiplication. Say for example 1 into minus I, which is exactly same as minus 1 into I, which is equal to minus I. And you see, if you take any combination, you would immediately see that the order of the combination is immaterial, and hence every element in the group commutes with each other, and such a group is called abelian group. Now let's go back and take our previous example of matrices. We have 6 matrices, and if we take the combination between B and C, that is the column element B and row element C, you can see that the product is F. Now take the combination between the matrix C and the matrix B, that is the column element C and row element B. The product is the matrix D. If you take the other way around, taking B multiplied by C, you would see that it is not D but it is F. And hence you can say that in the above group, elements do not commute with each other, and this group doesn't belong to abelian group. In fact, we say it's a non-abelian group. Now we will move on to another kind of group, which is called a cyclic group. I will explain the cyclic group with an example. Let's take the previous example of 6 matrices. And remove the last 2 columns and last 2 rows. You would get a smaller group, and we have seen that in fact this forms a subgroup of order 3. And we have 3 elements in the group, namely E, A and B. Now what I am going to do is, I am taking the powers of element A. Say if I take A to the power 1, which is exactly A to the power 2, which is A multiplied by A, which is A square. And if you look at the group multiplication table, you can see that A into A is B. Answer is B matrix. Now if you take A to the power 3, which is A into A into A, which is A cube can be written as A into A square. And we have already found out that A square is B, so it is A into B, which is equal to identity matrix, which when you go to the group multiplication table, you can see that it is identity element. Now you compare the result of powers of A, you can see that A to the power 1 is A to the power 2 is B, and A to the power 3 is identity element. So what I just shown here is, every element in the group is constructed from one element by taking its powers. Such groups are called cyclic groups. Now for the sake of curiosity, you can ask what is A to the power 4. A to the power 4 is A cube into A, and we have seen A cube is identity element, and so it is E into A, and the result is A. And therefore there is a maximum power you can see, which is usually the order of the group, beyond which the group elements gets repeated. That means if you take A to the power 5, what you are going to get is b. If you take a to the power 6, you are going to get the identity element back. Similarly, this gets repeated if you increase the power. Thus, in general, for a cyclic group, an element R exists in that group such that the element R to the power 2, R to the power 3, etc. up to R to the power h number of elements can be regenerated from R by taking its powers. And of course here R raised to h is identity element. So in the case of a cyclic group, there is an easier method to construct a group multiplication table. Say for example, if I take a group of order 3, we need to look for the elements like R, R square and R cube, where R cube is identity element. So if I write the identity element as the first element, you can construct a group multiplication table like this by taking E, R and R square. So first row is easy and first column you can immediately write. Now in the second row, the second element is R into R, R square, and the third element is R cube, and R cube is identity element. And in the third row, the second element is R cube, R into R square, which is R cube, which is identity element again, and the third element is R to the power 4, which is R. And if you now look at the group multiplication table, you can see there is an ordered arrangement of elements. Now bring back our previous example of 4 elements, 1, I, minus 1 and minus I. Test whether this is a cyclic group or not. So let R is equal to I. Now if I take the square of it, R square, which is minus 1. Now if I take R cube, which is R square into R square is minus 1, so it is minus 1 into I, which is equal to minus I. R raised to 4 now is R cube into R cube into R, which is equal to minus I into I, which is equal to minus 1. So you can see that all elements are regenerated by taking the powers of the element I. Therefore, this group also belongs to a cyclic group. And we have already seen that this group belongs to Abelian also. So this group is cyclic as well as Abelian group. Now you can prove that all cyclic groups are Abelian. If you have a cyclic group, which is definitely Abelian. This is because the power of any element always commutes with the power of any other element in a cyclic group. And thus all cyclic groups are Abelian. But the reverse is not always true. That is, not all Abelian groups are cyclic. We will prove this statement later when we discuss the molecular symmetry elements and their groups. Now, so far we have seen that in a given group, it may be possible to select various smaller sets of elements. And one example is, in the last case we have discussed subgroups, in which a smaller group including the identity element itself forms a small group. And that's what we said, it is a subgroup. So defining a class is another way in which elements of a group may be separated into smaller sets. And these sets are named as classes. So in defining a class, it requires defining an equality called similarity transformation. So first let us see what is similarity transformation. Suppose that I have a group of elements A, B, X, etc. Then the element A is said to be conjugate to element B when they are related as A is equal to X inverse BX. And this transformation is called similarity transformation. Here, the element A is said to be similar to element B under the element X. Now this says A and B are conjugate elements. So if A is conjugate to B, the vice versa is also true. That is, if A is similar to B, B should also be similar to A, and it is very easy to prove. Take the previous equation, left multiply the equation with X on both sides, and right multiply the equation with X inverse on both sides. You should always keep in mind that these elements do not in general commute with each other. So left multiplying with X and right multiplying with X may be different. So if you do that, we know the relationship X into X inverse is identity element, and this immediately leads to the equation XA X inverse is equal to B, which says B is also similar to A. B is a similarity transform of A. So having said that, let me define a class. A class is a complete set of group elements that are conjugate to one another. That means if you have some, say, 6 elements, there may be 3 elements which are conjugate to each other. Then we say all these 3 elements form one class. Similarly, if the other 2 may form another class. Sometimes a single element forms a class of itself. This is usually the case with identity element. Identity element always form a class of itself. Now you may ask, why is class important? There are many reasons. And the first one is, it is another way of separating elements into smaller groups. So separating into smaller groups can be done using classes. Now the second one is, it enables us to identify some of the important properties of a group. Later when I discuss the mathematical preliminaries of matrix algebra, you will there see that a symmetry operation can be written in terms of a matrix, and if 3 matrices are similar in terms of similarity transformation, then they all have same traces. So the third one is, it says the same thing, elements in a class behave similarly. Now one example, as I said, it will have the same trace. So these class of elements can be dealt as a group, and hence it reduces much of mathematical complexity. Now in the end, I should answer how to find the classes in a group. The only thing you have to do is to work out all similarity transformation for each and every element in the group. Say for example, if I take an example of a group of order 6 with elements E, A, B, C, D, F, and this group multiplication table is taken from F.A. Cotton's book. Now we have the elements E, A, B, C, D and F. Now I will tell you how to find out the number of classes in a group and what are the elements including each class. So let us take it as a step-by-step procedure. In the first step, what you have to do is you have to find the conjugate elements of E with all other elements. That means you have to do similarity transformation of E with all other elements. And doing this is a trivial exercise because the element is identity, combination becomes much simpler. So what you have to do is, you have to take inverse EE, then you have to find out A inverse EA, that is with the second element. Do the same thing with third element B, fourth element C, fifth element D and sixth element F. And this E is sandwiched between an element and its inverse. All calculation leads to identity element. What it says is this: the element E, that is the identity element, constitutes a class of itself. So we found out a class with only one element E. This is the case with every group. Every group forms a class of identity itself. Now in the second step, what you have to do, take the second element is A, and find out the similarity transformation of A with every other element including A. So first case is simple because on both sides it is identity element. Inverse of identity is identity itself. So it comes out to be A. Second case, you see that it is A inverse A. A inverse A is identity. Then identity multiplied by A is A itself. So it comes out to be E into A is equal to A. And in the third case, what you have to do is you have to first find out the inverse of B. How to find out the inverse of B? Go back to the group multiplication table and find out which element when combined with this B gives identity element. If you see the group multiplication table, you immediately identify the inverse of B is B itself. So it becomes BAB. Now what you have to do? Now you have to find out the result of the combination AB. Again go back to the table. And it is AB. You see AB, then A should be the column element, B should be the row element. So the column element A and row element B intersects at the element F. So the answer is F. So this becomes B into F. Again go back to the group multiplication table. Find out the intersecting element between B and F. B should be the column element, F should be the row element. So the answer is C. Similarly, you do the similarity transformation of all the other three, and ultimately you will find out that the fourth one is B, fifth one is also B, sixth one is C. You can do it yourself. and see the result. What are the results that we have got? First one is A, second one is A, third is C, fourth is B, fifth is B, and sixth is C. We have got three elements, that is A, B, and C. And this confirms that the elements A, B, and C forms a separate class. But we have so far carried out the transformation only for A. Now if you try the same procedure with B and C, you will get the same result. You will ultimately get the same result. If you find the similarity transformation of B, for example, you will again end up with A, B, and C. Similarly for the C element also. What it means is that the elements A, B, and C forms a separate class. Now what next you have to do? We need to find out the two more elements, that is D and F. So you do it as an exercise. You will come up with a result that this D and F forms a separate class. So we have three classes in this group, namely identity element forms a class of itself. Order of the class is 1, that is, there is only one element. Then we have a class of order 3 with elements A, B, and C. And the third class contains two elements, D and F. Now look at the order of elements. What is the order of the parent group? Order of the parent group is 6. So there are 6 elements. And if you compare the order of the classes, you will immediately see that order of the classes are factors of 6. That is the order of the parent group. This is in fact always true for every group and its classes. So what it says order of the class must be an integral factor of the order of the group. Now if you are getting a fraction instead of a whole number as the order of the class, that means you have done a mistake somewhere. You have to go back and correct it. So that is all about today's lecture. So whatever I discussed is abstract mathematics. Now in the next lecture I will show you how this abstract mathematics of groups can be applied to the molecular point groups. So thank you for watching my video. If you have any feedback, please put it in the comment box. Thank you very much.